Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, in the last lecture, if you recall, we talked about the failure criteria, the von Mises failure criteria as well as Tresca failure criteria. So, those two things we have discussed, and there at the end actually we just talked about engineering strain and true strain, right. So, basically what does it mean? So, first, if we look at the engineering stress strain, basically what does it mean? Why they are different? Why you are getting some different terminologies like engineering stress strain and true stress strain? So, what exactly does it indicate? Okay. So, suppose you are doing some, or you are taking some uniaxial member and you are applying some force, tensile force here, and due to that action you will be getting some elongation in that member, right. That is the common phenomena in the deformable body, and the original length of the member say L naught and original say cross sectional area of the member say A naught. Okay. Now, if this increase in length is a delta L, then basically your sigma, as far we were discussing, so far we have discussed whatever. So, that sigma, that is the normal stress, right. Normal stress is nothing but F by A naught, right, and your normal strain is given by delta L by L naught, right. Now, the way you are getting the stress, that tells you that we are not changing the force F during the experiment or during the test, but however, as you know, due to the Poisson effect, when you are pulling it, when you are getting some increase or elongation in the member, you will be getting the reduction in the area, cross sectional area, A naught will be getting reduced, but that we are not considering. We are considering, when we are calculating the stress, we are considering the stress based on the original area A naught, right. Similarly, when we are calculating strain, at that time delta L is the final elongation of the member, but this L naught, this strain is nothing but a continuous process, right. You are applying the load, you are increasing the load, and the elongation is going on increasing, right. But still we are considering the original length of the member, and based on that we are calculating the strain. So, these strains whatever, or these stress whatever we are getting, these stress strain both are known as engineering stress strain. Then what is the true stress strain? So, when we are talking about the true stress strain, because why I am saying true, why? So, that means the engineering stress strain are not true, they are basically some kind of based on the original configuration, right. So, they are not giving you, frankly speaking, they are not giving you the actual response or actual figure what is happening during the process of the test, right, during the process of the application of load. But that if you want to capture at that instant what is happening, if you want to capture that thing, then you have to talk about true stress strain. So, in the true stress strain, basically the strains may be large, right. If you are considering strain is large, and then if you calculate engineering strain, basically that will not give you the correct picture, right. If as long as your strain is very small, then you can still think of the original I mean you can still think of calculation of the strain with respect to the original length. But if your strain is very high, then this will be giving you very approximate value, right. So, the true stress strain, basically the strains may be very large, and if the strain is very large, then basically you can consider the total strain is defined as the sum of incremental strain. Incremental strain, that is a delta epsilon bar. Okay. So, we are defining the true strain as epsilon bar. Okay. So, therefore, your true strain epsilon bar is nothing but summation of your incremental strain, that is your delta epsilon bar, okay, which I can write summation of delta L by L. What is L? L is the length, L is the current gauge length. Okay. So, at that instant when you are considering that particular increment, right. So, we can write down that where L is the current gauge length when the increment of elongation or contraction, whatever you consider depending on the type of loading, delta L occurs. Okay. So, where L is the current gauge length, that at that particular instant what is the gauge length, you are defining the strain based on that. Okay. Current gauge length when the increment of elongation or contraction depending on the load, whether it is tensile load or a compressive load, delta L occurs. Okay. So, that we can write down. So, if your L naught is your initial gauge length, and say LF is your final gauge length, then basically your true strain can be expressed as the integration L naught to LF dl by L, right, very clear. I mean there is no doubt for that. Okay. So, that if you do, you will be getting that will be ln LF by L naught. Okay. So, because logarithmic base E is coming, so therefore, sometimes in some book it is called as logarithmic strain, logarithmic strain. So, logarithmic strain is nothing but true strain. Okay. In some book you will be getting this term logarithmic strain. So, true strain or logarithmic strain both are same, understood. So, this is the value of or the expression of true strain. It is not very simply delta L over L naught. Okay. So, it is a continuous, I mean continuously or continually you are getting the increment or the elongation, and based on that you are calculating the strain. Okay. Similarly, you can calculate the stress, that means true stress. So, true stress, that sigma bar we are saying, okay, true stress is given by F by A, not A naught. Okay. In case of engineering stress, we calculated engineering stress equal to F by A naught, but here it is F by A. Now, what is A? A is instantaneous cross sectional area. As I told you that when you are pulling the bar or the pulling the say member, right, your cross sectional area is reduced, getting reduced, right. If you are compressing the bar or the member, your cross section would be getting increased. So, depending on that, at that particular instant, okay, what is the cross sectional area, if you consider that, and based on that if you calculate the stress, then that stress is nothing but your true stress. Okay. So, it is not based on your original thing. So, it is taking care of the instantaneous picture of the system or under the load. Okay. So, that your sense your this plastic strain or whatever strain you are whatever say strain you are observing due to during that period, actually your volume is not getting changed, right. I am not changing the volume of the material, right. When you are applying the force, your volume is not getting changed. If your volume is not getting changed, then I can write A naught L naught, where A naught as well as L naught are the original dimensions, must be equal to A into L at any instant during the test. Whatever cross sectional area you are getting and whatever length you are getting, gauge length you are getting, they must be same, because we are not changing or we should not expect any change in volume, right. So, from and your L is that at particular instant your L is given by L naught okay, L naught plus epsilon into L naught, right. So, that is your gauge length at any instant. Okay. So, that can be written as, this can be from here I can write A naught by A is equal to L by L naught is equal to 1 plus epsilon, that is strain. From this I can simply write, now this is your true stress, therefore, true stress is nothing but F by A, can be written as, in place of A I am writing in terms of A naught, okay, F by A naught 1 plus epsilon. Okay. Now, what is F by A naught? F by A naught is nothing but your engineering stress. So, this much is the difference coming between the true stress and the engineering stress. Understood? So, this is your true stress, this is your true stress, and this is your engineering stress. Okay. So, this is the factor should be multiplied with the engineering stress to get the true stress. Okay. Now, if you plot the true stress versus true as well as engineering stress versus true as well as engineering strain, then how it will look like the stress strain curve. So, this is your strain, this is your stress. Now, you this is your true stress strain curve, this is your engineering stress strain curve, and you are getting the fracture in tension. So, suppose you are applying the tensile force, so you will be getting fracture at that point, okay, and here you will be getting fracture at that point. So, now if you look at, so up to this point, say both your engineering strain, that means as long as you are dealing with a small strain problem, then engineering strain and true strain will not make much difference, right. As long as you are within this range of strain, okay, you see that same curve, true strain and engineering strain both are predicting almost similar behavior or similar amount of strain, right, or stress strain behavior. But after this point, suddenly your engineering stress strain follows this path, whereas the true stress strain is following this path. Now, if you look at this region, actually, if you define your stress strain behavior based on your engineering stress strain behavior, then after this point basically you are not getting this much of extra stress happening in the material. So, that approximation, engineering stress strain approximation is basically giving you some conservative, some at a particular strain you are getting much higher stress if you talk about true stress strain, right. So, that is why I mean in this particular course also we will be sticking, and there I mean basically we are also considering the small strain problem in this particular course. So, therefore, we will be sticking to the engineering stress strain. So, we are not we will not be talking about much about the true stress strain. Okay. I hope it is clear. So, with this I conclude this chapter, that is your stress strain and temperature relation. Now, we will take a few numerical problems to understand whatever we have learned so far in this particular chapter. Okay. Okay. The first problem we are taking here. So, if you look at the slide, the first problem tells that a long thin walled cylindrical tank of length L just fits between two rigid end walls, okay, when there is no pressure in the tank. Now, estimate the force exerted on the rigid walls by the tank when the pressure in the tank is P, small p, and the material of which the tank is made follows Hooke's law. So, let me draw the figure. So, basically you have two end walls and you have a very thin walled tank which is just fitting between the end walls, okay. And now this is the thickness of the wall, this is the length of the tank as given in the problem L, and this direction, say this is Z and this is theta, theta is something like your circumference, that is a hoop direction, okay. And the 2r is the inner diameter of the tank, and this is under internal pressure P, okay. So, problem says that if you go back to the problem says that the tank is, I mean tank just fits between the two rigid end walls when there is no pressure, okay. It is just fitting between two walls, okay. Now, estimate the force exerted on the rigid walls, okay. So, this is the force exerted on the rigid walls as shown here when you are applying some internal pressure P inside the tank, okay. Now, I mean if you recall the discussion whatever we made for thin walled pressure vessel, okay. So, that idea or that concept will be required here to find out the stresses, okay. I mean stress components rather in different directions, okay. So, I am not going to derive that thing, because if you apply the concept of thin walled pressure vessel, then basically you will be getting the stress components in all directions, that is sigma z, sigma r and sigma theta. So, basically you have three directions, right, in the polar coordinate system, z, r and theta. So, you will be getting the stress components, you can calculate or you can determine the stress components, okay, in all three directions. So, that thing I am not going to do, because that you can perform or you can do by using the theory whatever we have developed for the thin walled pressure vessel earlier, okay. So, we will be taking that thing directly, I mean that magnitude of the stress components we will be taking in this problem directly, okay, fine. So, now if you look at this problem, it is very much clear from the figure itself, because these two are the rigid walls. So, your epsilon z must be 0, that means the deformation or the strain, okay, in the z direction is simply 0. right, because the rigid walls will not allow any kind of deformation in the z direction. Okay. So, that is my say geometric fit you can say. Now, considering the say free body diagram, I am considering one say section here, section 1 okay. In that section 1 if I draw the free body diagram, so that will look like say okay. If you consider one section 1 like this and you are taking you are drawing the free body diagram of both the parts. So, this is the left hand side part and this is the right hand side part. Now, at section 1 if you look at, if you consider one plane okay, one z plane rather. So, on that z plane you are having this internal pressure is giving the force okay, that small p will give you the force if it is a circular, because this is a circular tank. So, on the circular cross section it will be applying the force okay, and this will be the force because this tank will give the thrust on the wall. So, therefore, wall will be giving one opposite equal and opposite reaction on the tank. So, that is shown here, that is F, and that has to be calculated actually, that is the objective. And under this action of force and reaction and all those things, external force, you will be getting some force will be developed along the wall, right. Otherwise, this R will be, that is something like your tangential force. If you have the hoop like that, I mean tank like that, so it will be tangential to the tank okay. And if you similarly if you consider the right hand side of the tank, this R should be equal and opposite, as you know from your discussion, and of course, we will not be having any force in the radial direction by following the same argument whatever we did when we talked about the thin walled pressure vessel, right. If you have the radial direction force, then basically you are disturbing the symmetry, right. So, by following the same argument we can consider we can say that there is no radial direction force okay, fine. So, under now if I consider this part left hand side part, then I can consider the equilibrium. Considering equilibrium, I can write F plus R okay, both are in the same direction, positive z direction, is equal to P into pi r square. Pi r square is nothing but the cross section area on which the internal pressure is acting okay. So, from this I can simply get R equal to pi P r square minus F okay. So, therefore, your axial stress in cylinder, axial stress in tank, that is your sigma z is nothing but R, that is the tangential force okay, in the z direction force, R divided by the area. Now, what is that area on which R is acting? 2 pi r, that is the circumference, multiplied by thickness t, as simple as that. Okay. So, this is nothing but by putting this value pi p r square minus f divided by 2 pi r t. Okay. Now, circumferential stress. Okay. So, these things we are taking from our previous discussion. I mean, even if you solve the thin wall pressure vessel, so these stress components you will be getting. I am not proving or I am not determining that thing again in this particular problem. However, that you can get by following the same theory whatever we have talked about for thin wall pressure vessel. So, the circumferential stress will be this, you can calculate or you can determine for thin wall pressure vessel, that should come like that. Okay. And your sigma r should be approximately 0. So, these two components you will be getting from the theory of thin wall pressure vessel, that you can determine by following the derivations, okay, whatever we did for our thin wall pressure vessel. Anyway, that we are not repeating here. Okay. So, we have got 3 stress components, sigma z, sigma theta and sigma r. So, now our stress strain relation, if we invoke, then we will be getting epsilon z is equal to, by following, because this material is following the Hooke's law, sigma z minus nu into sigma r plus sigma theta, which is nothing but 0. Already we have seen that, because your wall is not allowing, both the walls are not allowing the movement in the z direction. So, from this I can write sigma z equal to nu into sigma r plus sigma theta. Okay. Now, by putting the values here, now by putting the values of sigma z, sigma r and sigma theta, we are just getting like this, pi p r square minus f by 2 pi r t, that is your sigma z, I mean yes, sigma z into nu, that is Poisson ratio, into p r over t, because sigma r is 0. So, this is only the sigma theta. So, from this you will be getting f equal to p pi r square 1 minus twice. This is the force exerted by the tank on the wall. Okay. So, if you want to design your wall, so wall should be designed for that much of force F. Okay. So, you have got that. Okay. So, I hope that you have understood the steps involved in this particular problem, and therefore, I mean and I mean whatever process, I mean by following the geometric fit and all those things, you just got this force, because epsilon z is 0, and based on that you can find out this. Okay. So, I will stop here today. Okay. In the next class we will be continuing another couple of numerical problems. So, thank you very much.